Hello, and welcome to today's webinar, PFAS, Exposure and Health Outcomes. I am Dr. Barbara Malkas, Board President for Massachusetts Breast Cancer Coalition, and I'd like to thank you all for joining us today. Massachusetts Breast Cancer Coalition is dedicated to preventing environmental causes of breast cancer through community education, research advocacy, and changes to public policy. I am pleased to welcome today's speaker, Dr. Laurel Schaider. Dr. Laurel Schaider is a senior scientist at Silent Spring Institute, where she leads the Institute's water quality research on PFAS and other contaminants of emerging concern. She studies PFAS chemicals in drinking water, consumer products, and food, drinking water contamination from septic systems, and environmental justice disparities in drinking water quality. Dr. Schaider, welcome to today's webinar. I'm sure you're going to have a lot of information for us. And if you are thinking of a question or a question comes up for you, feel free to put it in the box marked questions. Click on the icon and it will have a drop-down menu, and you can add those questions as we go along. And after Dr. Schaider finishes her presentation, we will get those questions answered for you. Thank you, and ready to start, Dr. Schaider?
Perfect. Thank you so much, Dr. Malkas. It's always a pleasure to be here with MBCC. I appreciate this opportunity to talk with all of you about PFAS today. My topic is very broad. PFAS exposures and health is a really broad topic, and we could spend many hours talking about this. And thinking about what to talk about today, I've tried to thread together various types of information that I hope will be of interest to MBCC followers, folks in Massachusetts, and really anyone with an interest in PFAS. So hope that all of you will learn something new today. First, I wanted to introduce you or reacquaint you with Silent Spring Institute. We are an independent nonprofit research organization with a mission to better understand links between chemical exposures and health, with a particular focus on women's health and breast cancer prevention. We were founded nearly 30 years ago by visionary activists from the Massachusetts Breast Cancer Coalition. They recognized the need for more research to better understand environmental causes of breast cancer, motivated by elevated rates of breast cancer on Cape Cod here in Massachusetts. We continue to work really closely with our partners at Massachusetts Breast Cancer Coalition, and we now are a leading scientific research organization focused on environmental causes of breast cancer. So the topic for today is PFAS. When I started working on PFAS back in 2009, there weren't really a lot of news articles, there were no Hollywood films focused on PFAS. And now every day in the news, locally, across the country, and around the world, PFAS are making headlines. These are some headlines from earlier this year on PFAS in tap water in the US, PFAS fish consumption advisories. Here in Massachusetts, I grew up in Concord, Massachusetts, near Walden Pond, and that was one of the ponds that issued a fish advisory by the State Department of Public Health to limit fish consumption. There's legislation that's being considered here in Massachusetts and in other states to ban PFAS in consumer products and other items, and increasing awareness of the waste stream, such as composting, as possible sources of PFAS into the environment. So for today's presentation, I will start with a PFAS 101. My guess is many of you are already pretty familiar with PFAS, but for those of you who are newer to the topic, I wanted to provide an overview of what these chemicals are, where they come from, and why they're of concern. I'll talk about how we assess PFAS exposures and who's most vulnerable, provide some updates and highlights on what we know about how PFAS can affect our health and how the EPA is responding in terms of developing drinking water standards. Through my work, I talk with many people in PFAS impacted communities, so wanted to talk about some of the concerns and needs related to health effects for PFAS impacted community members and how to meet those needs. And I try to end every talk with something about what you can do in your life to reduce your exposures and reduce the problem with PFAS more broadly. So PFAS 101, PFAS is an acronym that stands for per and polyfluoroalkyl substances. It's not just one thing. According to the EPA's most recent estimate, there are over 14,000 different chemical structures that are classified as PFAS. Some of these are big, long polymers like Teflon or PTFE. Some of them are smaller molecules that we frequently find in drinking water and in people's bodies. They've been cleverly dubbed forever chemicals rather than fluorinated chemicals because of their carbon-fluorine bonds. They tend to resist degradation out in the environment and in our bodies. They are very mobile in the environment. They've been found in all corners of the globe, even in the blood of polar bears at the Arctic, far from where these chemicals are used or manufactured. And we'll talk in a minute or two about the types of products that contain PFAS, like Teflon pans and Scotch-guarded carpets. And you might wonder to yourself, those have been around for many years. Why am I just hearing about them? Why are they just now getting so much attention? And I think it's an important point that these are not necessarily new chemicals, at least the older chemicals like PFOS and PFOA, we'll talk about those. But what's really motivated so much concern and attention is the widespread discovery of PFAS in drinking water supplies starting in around 2010 to 2015. And that has really led to so much advocacy, so much scientific research, and so much emphasis on regulation and policy. I'm not going to do a deep dive on the chemistry of PFAS today, but I did want to acquaint you with two of the most infamous PFAS chemicals up here in the upper right-hand part of the screen: PFOA, sometimes called C8, and PFOS. This blue zigzag here is the carbon backbone of this molecule, and all of these Fs are fluorine atoms. So these two molecules are nearly identical. I've just highlighted that they have a different part here on the end. And that affects how they can be toxic in our bodies and how they move around in the environment. And to learn more about PFAS, I do recommend you watch the film Dark Waters with Mark Ruffalo and Anne Hathaway, which focuses on a community in West Virginia contaminated by a DuPont plant that manufactured Teflon, and the heroic efforts of a lawyer to bring justice for the community and a massive lawsuit that led to the C8 health study. So PFAS are found all across the country. This is a map developed by our colleagues at Northeastern University with the PFAS Project Lab. This is showing locations across the country with known and potential sources of PFAS contamination. Some states like New Hampshire and New Jersey and Michigan have done extensive testing, so we have a lot more information to kind of fill in those dots about where PFAS have been found. But there are many other places across the country where PFAS have been found and where they're likely to show up based on locations of certain types of businesses or industries or waste distribution sites. So how do PFAS move around in the environment, and how do people get exposed? So PFAS are synthetic chemicals. So all of them are produced at a chemical manufacturing plant. They can also be incorporated into many different types of products. So for instance, in Merrimack, New Hampshire, there's a St. Gobain plant that uses PFAS produced elsewhere to create PFAS coated materials. So from these industrial sources, there can be emissions that contaminate the local environment. One other common pathway for PFAS to get into the environment are a class of firefighting foams called AFFF, aqueous film forming foam, and groundwater near military bases, airports, and fire training areas often contain high levels of PFAS. PFAS can also move through the environment through the waste infrastructure. So wastewater treatment plants and septic systems can release PFAS in their effluent as well as landfills. So PFAS can end up into the environment, and then we can be exposed in several different important ways. One way is through drinking water, and as well as from food. So the plants and the animals that we rely on for food can absorb PFAS from their surroundings or from their prey that they eat as well. Infants can also be exposed through breast milk and during pregnancy. So we can be exposed from water, from food, and then also from consumer products. So many everyday products in our homes and workplaces and schools contain PFAS. PFAS are widely used because they can lend certain useful attributes to products. They can make products non-stick, stain resistant, waterproof, and grease proof. So they're found in many kinds of textiles like stain resistant carpets and furniture, waterproof jackets, non-stick pans. They're used in grease proof food packaging like microwave popcorn bags and non-stick pans. And they show up in a lot of places where you might not expect to find them as well, like ski and floor waxes, cosmetics, dental floss, paints, and many other applications. My own work at Silent Spring Institute initially started on PFAS in 2009 and 2010 when we discovered PFAS in public and private drinking water wells on Cape Cod as part of a broader investigation of unregulated drinking water contaminants. And drinking water continues to be a main focus for my work, but I've also contributed to understanding PFAS exposures through food and consumer products as well. To name a few here, we led a study in 2017 showing PFAS are common in fast food packaging across the country. We analyzed data collected by the Centers for Disease Control and Prevention to identify that people who rely more on microwave popcorn or more food from restaurants tended to have higher levels of PFAS in their blood, suggesting that food packaging is an important source of exposure in the general population. We also found that consumer product use, such as stain-resistant carpets in the home and Oral-B Glide dental floss use, were associated with higher levels of PFAS in blood. And then a study last year that I talked about during our webinar back in the fall of 2022 found that many stain-resistant and waterproof children's products, bedding, clothing, and furniture also contained PFAS. So I want to talk now about how we get exposed to PFAS and who's most vulnerable to PFAS exposures. So an important thing to keep in mind is that PFAS exposures are widespread. So we've learned that they're common in many products. They're showing up in many people's drinking water supplies across the country. And they can also accumulate in our bodies. So testing conducted by the Centers for Disease Control and Prevention as part of a study called NHANES, that's the National Health and Nutrition Examination Survey, has found that in virtually every sample that they've collected as part of this study, people have measurable levels of at least one PFAS chemical in their blood. This is because certain PFAS are very long-lived in the human body. So what we call long-chain PFAS, like PFOS and PFOA, can stay in our bodies for years, what we call a half-life in blood. That means that if you stopped being exposed to any more PFAS or PFOA, it would take years for the level in your blood to go down by half. And then that same amount of time for it to go down by another half. Certain PFAS, like PFOS and PFOA, have been phased out of production in the US, and in their place are other PFAS. Some of these are short chain or other variations on the chemistry. These newer PFAS have not been as well studied in terms of their half-life in the body, but for the ones that have been studied, they do have shorter half-lives than the long-chain PFAS, more in the order of weeks to months, but that's still not really rapid clearance from the body. And on top of that, we know that we are exposed in many different ways in our daily lives. So you might wonder, in general, who tends to have higher levels of PFAS? So certainly people who get exposed at work, so people who work at chemical manufacturing plants or firefighters can have elevated exposures through their workplace. In general, older people tend to have higher levels than younger people because these chemicals can accumulate over our lifetime. And furthermore, men on average tend to have higher levels than women. This is due in part that PFAS bind really tightly to proteins in our body, in our blood, and women lose a certain amount of blood through menstruation, and so that is a way for the PFAS to be removed from the body. We also know that PFAS can be passed along during pregnancy and breastfeeding. So unfortunately, that means that babies are born pre-exposed to PFAS already, but that does mean that the levels in women's bodies or mothers' bodies tends to be lower. So PFAS are widely used in consumer products, and one thing that we've learned in our research and other researchers have as well, we know that chemicals in products don't stay in products. They can migrate out of the products and end up in the dust in our homes. So we don't typically think of dust as a important toxic chemical exposure pathway, but it can be a place in our home where these chemicals can accumulate. Certain PFAS are also volatile, so that means they end up in the air that we're breathing in as well. So we can be exposed to PFAS and other chemicals from products through inhalation, both of air as well as dust that's suspended in the air. We can ingest dust as well. We don't think about it, but we ingest a little bit of dust every day. And if you happen to be a kid and you put things in your mouth and chew on them, you can also be directly exposed to the chemicals in the products that way. And then if we're thinking about things like PFAS in cosmetics or other personal care products, those chemicals have the potential to be absorbed through the skin as well. Work by our team at Silent Spring and others have found that the presence of PFAS in consumer products and furnishings has been linked to higher levels of PFAS in blood. We also know that infants and children can have higher exposures to PFAS and other toxic chemicals from consumer products. And this is for several reasons. One is that children drink more water, eat more food, and breathe more air per unit body weight. So the chemicals can, think about them being more concentrated in their smaller bodies. Especially young kids, infants crawl around on the floor, and they lick their hands a lot, they put everything in their mouth, so there's a lot of potential for transfer of chemicals from products directly into mouths, from hands, and through dust. And in addition, as I mentioned, PFAS do get passed along during pregnancy and breastfeeding. I think it's also important to think about other populations and communities that may have disproportionate exposures to PFAS and other toxic chemicals. I was co-author on a paper that was published earlier this year that found that public water systems serving higher proportions of Hispanic and non-Hispanic Black residents were more likely to have detectable levels of PFAS. PFAS can also accumulate in fish and shellfish, and so subsistence fishers and members of Native American tribes can be exposed to elevated levels of PFAS through consumption of local fish, shellfish, and wildlife if they are in an area where there's PFAS, environmental contamination. One of the studies that I'm working on, the STEEP Superfund Research Program, is looking at PFAS in fish and shellfish on Cape Cod in a part of the Cape where there is known to be groundwater contamination of PFAS and is an area frequently used by members of the Mashpee Wampanoag tribe. And then it's also important to remember that when we provide advice about buying different types of products that are less likely to contain PFAS, these often are more expensive, and for people on limited means, it can be difficult for them to be able to buy greener products, safer products, to swap out products or furnishings in their homes, and they may have less ability to switch jobs if they're concerned about chemical exposures at the workplace. So we've talked a bit now about PFAS exposures, how these chemicals end up in our bodies, and who may be relatively higher exposed to these chemicals. So let's talk now a bit about what this can mean for our health. First, I wanted to talk a little bit, step back and think a little bit broadly, how do we actually learn about which chemicals are toxic and at what levels? And there's three general lines of evidence or three types of studies that we can learn this information from. So one type of study is called an epidemiological study. So these are studies that are conducted on communities of people that have been exposed. In the case of PFAS, that can include the general population, again, because over 99% of us have measurable levels of PFAS in our bodies. So epidemiological studies have several strengths. The results are directly relevant to people because the studies are based on people, and they can take into account our unique human physiology. However, there are some limitations to epidemiological studies. When we do see links between chemical exposure and a certain type of health effect, it can be difficult to make sure that that health effect is really related to that one individual chemical. We get exposed to many different chemicals in our day-to-day lives, so it can be difficult to tease out the effects of one or a small number of chemicals. And the other drawback is that they take a very long time. Here at Silent Spring, we think a lot about breast cancer, and it can take decades between when we think a critical exposure occurs and when breast cancer may become apparent. And so there's a missed opportunity for prevention if we only are relying on epidemiological studies. The second line of evidence, and something that many drinking water standards are based on, are toxicological studies. So these are typically conducted on rodents or other laboratory animals. The benefits of toxicological studies are that you can make a direct link between one specific chemical and a certain health outcome, because you can completely control the animal's exposures over their lifetimes. It also provides the opportunity to study multi-generational effects as well. Some of the limitations are that the physiology of rodents, while overall is very similar to humans, there can be important differences. They don't take quite as long as epidemiological studies, but they are time intensive and expensive to conduct. And then the third type of study are what we call in vitro studies. So in vivo means that they take place in a living body. In vitro are lab-based studies. So for instance, you can have a plate with little wells, and you have receptors. For instance, if you want to study which chemicals might bind to an estrogen receptor. So it allows you to evaluate many different types of chemicals quickly. So that's obviously two very important benefits. Of course, the drawback is that it can be harder to link what happens in a test tube in the lab to what happens in our bodies. When we think about the three different types of studies, really when we're able to combine evidence from multiple types of studies, that really can increase our confidence that we have a good understanding of the types of toxic effects that certain chemicals can cause. I've talked about this a little bit already, but it's also important to think about the timing of exposures as well. And we know that our bodies are particularly sensitive or susceptible to harmful chemical effects at certain key points. So in the womb and early in life, we can be more vulnerable. Babies and infants can be more vulnerable to chemical exposures because their bodies are still developing. The gastrointestinal tract can actually have higher absorption of toxic chemicals than for older children and adults. And the liver and kidney are also still developing, and so there can be less elimination or excretion of toxic chemicals from the body. As our young bodies are developing and changing, chemicals can affect the development of key organs in the body in ways that they wouldn't have that effect in adults, since adults have already completed their development. And then when we think about puberty or pregnancy as well, this is a time where there are many hormonal changes occurring, and so chemicals that are endocrine disruptors can have disproportionate effects during those key developmental windows of time. So much of what we know about PFAS toxicity comes from both epidemiological and toxicological studies, and many different types of health effects have been associated with PFAS exposures. Some of these include increased cholesterol and risk of obesity. A really important effect that I've talked about in a previous MBCC webinar is immune system suppression, including suppressed vaccine responses. There have been a series of studies in the Faroe Islands led by Philippe Grandjean, formerly at Harvard, showing that children with higher levels of PFAS exposure have lower antibodies in response to routine vaccinations. And obviously this has raised concerns in PFAS impacted communities about what their exposures might mean with respect to COVID-19 as well. Other types of effects include changes in thyroid hormone levels, reproductive effects such as high blood pressure during pregnancy and decreased fertility, developmental effects such as small decreases in birth weight or changes in bone density, impaired mammary gland development in laboratory studies of rodents, and certain types of cancer, kidney, testicular, and prostate cancer. So you might wonder what organs are not affected by PFAS. Dr. Linda Birnbaum, the former director of the National Institute of Environmental Health Sciences, was quoted as saying, "Not only do we all have PFAS in our bodies, but we also know that PFAS affects almost every organ system." So the more that we study PFAS, the more that we learn that they can affect our health in many different ways. Thinking specifically about harmful health effects in children, these are some health effects that were identified in a systematic review conducted in 2017, as well as some other more recent epidemiological studies. So PFAS exposures in children can cause elevated cholesterol, decreased vaccine response, asthma, reduced kidney function, changes in thyroid and sex hormone levels, and delayed menarche, which is the age of first menstruation. Here at Silent Spring and at Massachusetts Breast Cancer Coalition, we are concerned about how PFAS may play a role in increasing breast cancer risk. And there are several lines of evidence that raise concerns that PFAS may increase breast cancer risk. One line of evidence is from studies in laboratory rodents showing that PFAS exposures, and specifically PFOA, can lead to delayed mammary gland development. In studies of exposed communities, PFAS exposures have also been linked to shorter duration of total and exclusive breastfeeding. Again, that's kind of consistent with the idea of impairment of mammary gland development and raises concerns about increased breast cancer risk. So I'm not going to get into all of the 14,000 different types of PFAS chemicals, but broadly speaking, a lot of what we know about PFAS toxicity have focused on long-chain PFAS. At the beginning, I showed you PFOS and PFOA. These are two of many members of that branch of the PFAS family. Because PFAS have now been replaced with short-chain and other alternative PFAS, it's important that we know more about how these newer PFAS can affect our health, but they have been far less studied. I wanted to point you to a really helpful resource called the PFAS Tox database. This database compiles information about many different PFAS chemicals and the number and types of studies that have been conducted. And so you can go to the database and find studies if you want to know more about how specific PFAS chemicals can affect the immune system or affect the thyroid or liver or kidney. So from the PFAS Tox database, I made this graph to show the number of studies that have been conducted on all these different PFAS chemicals. For PFAS and PFOA, these are not included in the PFAS Tox database, but there's over 1,000 studies both for PFAS and PFOA, both toxicological, epidemiological, and in vitro studies. And what I want you to take home just from this graph, so the blue bars are showing long-chain PFAS, and the yellow bars are short-chain and perfluoroether compounds. And you can see that most of these bars are blue, so most of the work has been focused on long-chain PFAS, and the short-chain PFAS have also been, each have been included in far fewer studies. So it's a huge gap because we know that we are now being increasingly exposed to these newer PFAS chemicals. But what we do know so far is concerning because these newer PFAS chemicals have been linked to some of the same harmful health effects as the long-chain PFAS that they're replacing. So I wanted to switch gears a little bit and think about how our increasing knowledge base on PFAS toxicity is being translated into regulations and specifically drinking water. So the last time that I spoke with the MBCC audience, we were waiting for EPA to issue draft drinking water standards for PFAS and PFOA, again, the two most notorious members of the PFAS family. This bar graph and this table are just showing the trajectory or the timeline for EPA's guidances on PFAS. So back when I started this work in 2009, EPA had issued draft drinking water or issued drinking water guidelines of 400 and 200 parts per trillion or nanograms per liter for these two chemicals. In 2016, they reduced that to 70 parts per trillion for the two chemicals combined, so almost an order of magnitude lower. And then last year, they issued updated health advisories, and at first I thought that I was looking at the wrong order of magnitude, well below 1 part per trillion, so 0.004 nanograms per liter or parts per trillion for PFOA, and 0.02 nanograms per liter for PFAS. This is just based on health information and really reflected that our increased understanding meant that of PFAS meant that really the near zero levels were the appropriate level for regulation. And then this year they issued draft drinking water standards of 4 nanograms per liter for PFAS and PFOA. It's important to keep in mind the 2022 health advisories were just based on health effects and didn't take into account cost or feasibility, or even if they were levels of the chemicals that could be measured. While the appropriate health guidance may be well below 1 part per trillion, labs can't routinely measure that low. So the EPA had to set draft standards at a level that could be routinely measured. But it is really striking to look at this more than 2 orders of magnitude lower levels of that EPA is looking at for regulating PFAS in drinking water. So in this past March, EPA issued draft drinking water standards. As I said, for PFAS and PFOA, the draft standard is set at 4 parts per trillion. They also had a MCLG, so this is a maximum contaminant level goal. Because both PFAS and PFOA have are likely to be carcinogens. For carcinogens, MCLGs are typically set at 0 because our understanding of how chemicals cause cancer is that there's really no safe level, there's no threshold. So their MCLGs for PFAS and PFOA were 0. And then for 4 other PFAS chemicals, some of which are long chain, some are short chain or perfluoroether compounds, they set a hazard index of 1. So you might wonder, what is a hazard index? So it's important that this is not a unit of part per trillion. It more has to do with ratios. Let me just explain that here. So what's a hazard index? Hazard indices allow regulators to consider multiple contaminants at a time and to combine chemicals even if they're have different potencies. So some chemicals are more toxic than others, and the appropriate standard is lower for more toxic chemicals, more potent chemicals. And so hazard indices are widely used in risk assessment, but this is the first time that they've been applied for drinking water standards. And I won't get too into the details of the math here, but basically for each chemical, again, 2 of the long chain, PFAS, PFNA, and PFHXS, PFBS, which is a short chain replacement for PFAS, and then GenX, which is a PFOA replacement. The concentration for each of those chemicals is divided by a health-based guideline value or benchmark, and then the sum of those is supposed to add up to less than 1. So it's supposed to take into account that we are exposed to multiple PFAS at the same time, and that these exposures are additive. So I wanted to talk just a little bit more about the basis, or what were the critical health effects that were used by EPA in setting these drinking water standards. Many drinking water standards are set on the basis of toxicological evidence, again, from laboratory studies of animals. For PFAS and PFOA, these were based on suppression of vaccine responses in young children. And this was a striking quote from the 2022 Lifetime Drinking Water Health Advisories documents, which indicated that some negative health effects may occur at concentrations of PFAS and PFOA that are near 0 and below our ability to detect at this time. For the other 4 chemicals that are included in the hazard index, again, some of these PFHXS and PFNA are long chain. GenX are perfluoroether compounds, so again, newer replacement chemicals, and PFBS is a short chain chemical. And these were based on different types of developmental and endocrine effects in laboratory animals. So switching gears a little bit in terms of updates on how we're learning more about how PFAS can affect our health. In previous webinars for MBCC, I've mentioned the CDC PFAS multi-site health study. So this is a large epidemiological study that's being funded and coordinated by the CDC and by the Agency for Toxic Substances and Disease Registry. This is being organized as a cooperative agreement with research teams in 7 different states, and each of the research teams are working with local communities where there's been contamination of drinking water supplies. And the broad goal is to understand, improve our understanding of PFAS health effects. So Silent Spring Institute is leading one of the 7 studies within this broader multi-site study. Our study is called the Massachusetts PFAS in Your Health Study, and it's taking place in Hyannis and in the town of Ayer. These are 2 communities where the drinking water supplies were contaminated by PFAS coming from AFFF firefighting foams. The other research partners on the project are the Harvard School of Public Health and Eastern Research Group. And then our local community partners are the Massachusetts Breast Cancer Coalition, specifically Cheryl Osimo, our key community liaison on the Cape, and People of Air concerned about the environment. So the last time that I spoke with all of you about the multi-site study, we were still recruiting participants. And now, as of the end of September, CDC was requiring all 7 sites to wrap up data collection by the end of September. So all in all, we recruited and enrolled 700 adults and nearly 100 children into our study. Our study had a few different components. One was a blood draw and a series of body measurements, a questionnaire to learn more about where people have lived and worked over time, their health history, and their water consumption patterns. And for children, we also conducted a series of neurobehavioral tests. There's not a lot of information about whether PFAS can affect brain development and things like learning and memory. So that's one of the questions that the study was designed to answer. So I will be sure to keep all of you updated in the coming years as we learn more from the data collection and what our analyses show in terms of health effects. In terms of other areas for future PFAS research, I think it's important that we gain a better understanding of the toxicity of newer alternative PFAS chemicals, again, short chain, perfluoroether compounds and others, and also to apply new statistical methods to better understand the effects of PFAS mixtures. We're increasingly becoming aware of PFAS exposures among firefighters and other workers, but there's still more work to be done to understand the extent of those exposures and the different occupations that might be associated with higher PFAS exposures. Kind of a newer area of concern is the potential for PFAS to be found in plastics. And so I think it's important to better understand the extent of exposures that might be occurring from plastics that have PFAS. We've thought a lot about drinking water quality, and rightly so. And with the new standards likely to be finalized by EPA probably early next year, there's going to be increasing awareness and ultimately treatment of PFAS contamination of drinking water supplies. I think it's also equally important to make sure that we're protecting people from exposures that might be occurring from fish, shellfish, hunting, and also homegrown produce. And then another area where there's really not a lot of research done yet, but would be really important, is to better characterize the extent of dermal absorption. So how much PFAS can move through our skin and which types of PFAS are most readily absorbed. So again, through the work that I've been conducting with our studies here at Silent Spring Institute, I've had the opportunity to get to know people in many different PFAS impacted communities. With respect to questions about health effects, some common needs, concerns, and questions are how people can get their blood tested for PFAS, understanding what the results of those blood tests mean, thinking about medical screening or medical monitoring. So what are kinds of tests that an individual's doctor might do to screen for types of health conditions that people might be at greater risk of. And then I hear a lot of questions too, about exposures that have happened in the past, people who have elevated PFAS in their blood, whether there's anything that they can do to reduce the levels of PFAS in their blood. So PFAS blood tests are the most common way to measure PFAS exposures. PFAS do accumulate in the blood because of their propensity to stick to proteins like albumin in the blood. Typical current blood tests mostly measure long chain or legacy PFAS, and some testing has found that the short chain PFAS are not present at those same levels in blood. Testing that's looked at organofluorine, so that's kind of a measure of the total amount of PFAS in samples, shows that there's a fair bit of PFAS in blood that we're not accounting for. And so that raises questions about what other PFAS are in people's blood that we're missing. There was just a study that came out earlier this year showing short chain and ultra short chain PFAS. So these are 2 and 3 carbon chain compounds, and found that they were actually pretty commonly measured in people's blood. So we're starting to get a better handle on the full range of PFAS exposures, but there's still a lot of work to be done and more analytical techniques to really allow us to measure all of these different types of PFAS at the levels that are typically found in blood. I also wanted to highlight a report that was published last year by the National Academies of Sciences, Engineering, and Medicine. This was a panel that came together through a request from the Agency for Toxic Substance and Disease Registry, or ATSDR, and NIEHS, the National Institute of Environmental Health Sciences, seeking guidance on how to develop better recommendations relating to PFAS exposure, testing, and clinical follow-up. So, and we've talked about this before in previous NBCC webinars, but one of the really striking and noteworthy outcomes from this report was the recommendation that clinicians should offer PFAS blood testing to patients who are likely to have had a history of elevated exposures. And the report goes on to say that while physicians may worry that learning about PFAS exposures might cause alarm in people, that with the right context, with the right information, that this is valuable information that that people should have access to. It helps them get a sense of how their exposures compare to other people. It may provide them some information about health conditions that they might be at elevated risk of, and could be useful for future research studies as well, and for comparison to look for whether levels do change in an individual over time. So the National Academies panel did their own review of the scientific literature, evaluating which types of health effects had the strongest evidence of links to PFAS. So I just wanted to highlight here that many of these are similar to types of health effects found in other studies as well. So the highest level of confidence here, showing that these associations are unlikely to be due to chance or bias, relates to antibody response, dyslipidemia, again, elevated cholesterol and changes in other lipids in the blood, in decreased infant and fetal growth, and risk of kidney cancer. And then there are other types of health effects with a more moderate level of confidence. And I would note that among these are increased risk of breast cancer. So following this compilation and evaluation of the level of the strength of evidence for different health effects, the National Academies panel also developed recommendations for clinicians about types of tests or screenings that might be appropriate for people based on their level of PFAS exposure. And so these were the recommendations that came out of the National Academies panel. I'd say, looking at results from the NHANES testing of the general population, most people kind of fall in this middle category here, but about 8 to 10% of people are above this level of 20 micrograms per liter, or parts per billion. And so I find this NASEM report really helpful, because people who've had PFAS exposures often wonder, like, what are kinds of diseases might I be at greater risk of? What can I talk to my doctor about? Many of the types of tests and screenings that are recommended are within the standard practice of care anyways, but it is helpful for people and for clinicians to know what types of health effects to maybe keep an eye out for, and to know what types of conditions people might be at greater risk of. And just one more point related to this National Academies report. This report is going to inform new guidance to be developed by the agency for the ATSDR, the Agency for Toxic Substances and Disease Registry. So look for that new guidance to be coming out, I think, sometime next year. I also wanted to mention our PFAS Exchange website. This is a product of our PFAS Reach study, which is a collaboration with Northeastern University and Michigan State University, Mass Breast Cancer Coalition, Testing for Peas, and Slingshot. We have a whole resources page on our PFAS Exchange website, including resources for clinicians. I wanted to highlight our continuing medical education course, our CME course, focused on PFAS, which brings together voices from public health researchers, medical doctors, and impacted community members. So clinicians can take this course for credit, but you can also just watch the video and access the content that way. We've also developed our own medical screening fact sheets. that are intended to be informative for patients and to have foster a conversation with clinicians, similar to the NASEM report in terms of types of health screenings and lab tests to consider for people who've had elevated PFAS exposures. Our PFAS Exchange website also features a tool called What's My Exposure to help people interpret results of PFAS blood testing. And then I wanted to talk about this question that we often hear, which is, is there anything that I can do? I've been exposed to PFAS already. I have elevated PFAS in my blood. Is there anything that I can do to more quickly reduce the levels of PFAS in blood? Over time, levels of PFAS do go down as long as exposures are reduced. Unfortunately, there's no clinically recommended way to quickly lower PFAS blood levels. Obviously the first thing, the most important thing to do is to limit new exposures. If there's drinking water contamination or other known sources of exposure, to treat the water to reduce those exposures. There was a study published last year looking at plasma or blood donation in Australian firefighters, and it was found that those do lower PFAS levels, but I'd say we're still a ways away from that being any sort of routine clinical guidance for individuals. From the C8 study, which was conducted in the West Virginia community, it was found that people who are in that study and taking a cholesterol lowering medication called cholestyramine did have much lower levels of PFAS in their blood. But again, this is not a medication that is going to be routinely recommended for people to take just to lower their PFAS levels. It does have its own side effects. It's intended for lowering cholesterol, and it's actually not really widely used anymore. And it was also found that it was not effective for all PFAS, so it lowered levels of PFOS, but not PFOA. So I think this is important information for people to have, and there is increasing research looking into whether there might be ways to lower PFAS levels in the future. So wrapping up here, I wanted to leave with some thoughts about what you can do in terms of our individual exposures, our family exposures, our household exposures. There are some things that we can do. We can try to select textiles that don't have stain resistance, avoiding microwave popcorn and other types of food packaging, eating more fresh foods, and filtering your water if you know that there are elevated levels of PFAS in your water. I don't think that it should just come down to individuals having to take steps to avoid toxic chemicals when you're buying food or products for your home, but in the short term, there are things you can do to reduce your exposures. I think it can feel a little overwhelming because PFAS are in so many different things. And sometimes people ask me, what's the one thing I should do, or what should I start with? And I would say that there's not one perfect place for everyone to start. I would say adopting a mindset of asking yourself when you're buying products, do I really need this product? Do I really need say a tablecloth to be stain resistant, or can I deal with having stains in order to avoid having toxic chemicals in your home? And I'd say start with a change that you're easily able to make. If you want to know whether your drinking water has PFAS, you can call your water supply. Some states already have drinking water standards in place. In other states, there isn't routine testing, and but that would start after the EPA adopts or finalizes its drinking water standards. You can look at your water supply's consumer confidence report, which every public water supply is required to produce annually under the Safe Drinking Water Act. For those of you in Massachusetts, the state does have a data portal where you can access results for your public water supply, and the Environmental Working Group also has a tap water database. To reduce your exposures to PFAS and other toxic chemicals in your daily life, you can look at download the Silent Spring Institute's Detox Me smartphone app. The PFAS Exchange has fact sheets, data interpretation tool, and community map. I'd also point you to the STEEP Superfund Research Program's website as well, with tips and updates on STEEP research. Beyond our individual household purchasing choices, there are some other ways that each of us can get involved. As consumers, we can let retailers know that you want safer products. And we've actually seen a lot of action by manufacturers and retailers who are now making pledges to stop producing or selling products that contain PFAS. Broadly speaking, we can support stricter chemical safety testing. PFAS are just one of many types of toxic chemicals in products, and they're really a symptom of our systematic failure to adequately test chemicals for safety before they go into widespread use. You can learn more by attending events such as this webinar and sharing what you learn with other people in your daily lives. If you're in charge or you have influence over procurement policies for your workplace or for your town, you can that can be a way to amplify better purchasing decisions. So making a pledge to not have food packaging, for instance, that has PFAS at your workplace or at your school or in your town. And then you can find out about local organizations and about any legislation that is being considered in your state. So if you want to get more involved, for those of you here in Massachusetts, Massachusetts Breast Cancer Coalition has a great website and several campaigns right now related to 2 bills that are being considered here in Massachusetts. Clean Water Action is also actively involved with campaigns on those 2 bills. Across the country, to stay on top of what's happening with respect to state policies and regulations, I'd recommend visiting the Safer States website. And this is a list of other resources. Some of these I'm part of, some of these connected with, related to understanding PFAS exposures and various types of information to help you reduce your exposures and keep your community safe. So thank you very much again to MBCC for this opportunity. And now I try to end all my talks with a picture of my kids because they're really my personal motivation for doing this work. So thank you.
Thank you so much, Dr. Schaider. Oh, am I still muted?
I can hear you.
Oh, excellent. All right. So, you know, your presentations are always so informative, have so much information for us. A question came up for me around the idea that they resist degradation, right? PFAS are forever chemicals because they resist degradation. Are there conditions that would support an acceleration of degradation of PFAS in the environment?
That's a great question and a lot of a whole nother really active area of research. How do we get rid of PFAS? I would say a couple parts of a response to that question. So one part is that there are chemicals that are called precursors. So these are also PFAS chemicals. In the environment, they can undergo some chemical transformations, but the fluorinated part of their chemical structure doesn't really break down. So sometimes you might hear about breakdown of PFAS precursors. They turn into things like PFAS and PFOA. So the chemical part of their chemical structure that's fluorinated is still really persistent. I would say that under kind of regular environmental conditions, there's really not going to be degradation or really appreciable rates of degradation of those like fluorinated parts of chemical structures. In terms of water treatment and waste treatment, there are some options. High temperature incineration is a way to break down the chemical structures of PFAS. However, there's a lot of concerns about that being the sort of ultimate solution for getting rid of PFAS, because there are only a limited number of incinerators that reach those high temperatures. There's a lot of concerns about environmental justice and potential exposures in communities where incinerators are located, and just issues of transporting PFAS-containing waste over long distances. In terms of other research areas, for say a water treatment facility or maybe a landfill, there are newer options for breaking down PFAS chemicals, like supercritical water oxidation or different electrochemical options to really break those chemical structures down. So I think there will be more kind of tools in the toolbox in the future for breaking down PFAS. I don't know that there are a lot that are kind of commercially available and viable at this point in time. For treating drinking water right now, most of the methods rely on separating out the PFAS on a carbon filter or some sort of a ion exchange resin, which importantly gets the PFAS out of the water that people consume. But you're still left with the PFAS. And so right now it feels like a shell game where you have the PFAS and we're moving them around, and we don't yet have a lot of great options. But I think in the future there will be more options available. In terms of cleaning up the environment, though, I think it would be hard to apply those kinds of methods to like cleaning up a lake or a river or some large body of water.
Thank you. You know, I was also thinking about like, why was PFAS not considered as a toxic or carcinogenic substance by manufacturers, which has led to their sustained use in products? Where, like, when they were first initiating the use of PFAS, why wasn't there a concern of the potential toxicity and carcinogenic properties?
Wow, that could be a whole separate webinar as well. A few responses. I mean, when the PFAS chemicals were first manufactured, there really weren't any environmental regulations at that time. You know, starting in the 70s, there started to be more regulations: Clean Water Act, Safe Drinking Water Act, Toxic Substance Control Act. But there, you know, we don't do a great job of screening chemicals before they go into widespread use. Industry early on did know about the harmful effects and didn't share that information, and it has taken other scientists kind of a long time to catch up with that. And we're very slow at catching up and regulating chemicals in general. And again, I think PFAS is just the current chapter and really a long story of how we've failed to protect people from toxic chemicals.
Would you say that most manufacturers now have shifted to the shorter chain PFAS in their manufacturing just to avoid, you know, kind of the spotlight of PFAS?
So here in the US and in Europe, chemical manufacturers have shifted away from the long chain PFAS chemistry. Long chain PFAS are still manufactured in China. So in general, yes, there has been a shift towards short chain PFAS. Industry will say that polymers are different, that long chain polymers are too big. These are not chemicals that can be absorbed into our bodies. But I think it's important to think about the whole life cycle of the PFAS chemicals. So polymers are created from shorter chain, short blocks of PFAS coming together to make the longer polymers. And there are also concerns about exposures in the communities where these fluoropolymers are manufactured. And then again, thinking about the long-term disposal challenges of these as well. So yes, in the US, they've shifted away from using the long chain chemistry, but there's still a lot of concerns.
And then for my last question that I have for you is, since PFAS is associated with obesity and cholesterol levels, endocrine impacts, which are all like there's a lot of health effects just from identifying those factors. How can researchers distinguish the health effects that are due to exposure versus these other health factors that may lead to obesity, high cholesterol, and endocrine impacts?
Yeah, that's a great question. And unlike, say, asbestos, which was linked to a very specific health outcome, the types of health effects linked to PFAS exposure can be caused by many other factors as well. I think studies like the multi-site study do allow us to learn more about health effects in exposed communities of people because we can measure levels of PFAS in their blood, or we can estimate their past exposures based on where they've lived and worked and their reported water consumption. And so we can account for other factors like diet or family history. Statistically, we can take those into account, and we can say, holding those things constant for people with higher PFAS exposures, do they have an elevated risk of high cholesterol or any of the other types of health effects that we're looking at?
So fascinating. Thank you so much. And thank you for sharing your children with us, which I think is the motivating factor for many of us in doing our work. I'm just trying to switch screens here so I can get to my thank you. And I really want to thank all of our listeners today for joining us. For those interested, the recording of this webinar will be made available later today on the MBCC website at mbcc.org. We would like to wish you all a very happy Thanksgiving and holiday season. We hope that you'll keep MBCC and our very important mission of breast cancer prevention in mind this coming Giving Tuesday, with generous donations from our supporters, which allow us to continue our work. Have a good afternoon, and thank you again, Dr. Laurel Schaider.
Thank you, Dr. Malkas.